So really last time we were talking about conversions, equalities, and really dimensional analysis. So just a reminder that when you do have an equality like your 12 inches is equal to 1 foot, from any equality, this is where we can get our conversion factors, which are really just two fractions, where we put one unit over the other. And as we talked about before, again, we will not use, obviously, both conversion factors in a problem. Otherwise, we sort of undo our calculation. We do use whichever one that we need to use. And when we set things up with dimensional analysis, remember, it is really just opposites cancel, and there's very few things that you have to remember in terms of how to do the calculation. So obviously here, if we had 22.5 feet and we wanted inches, we would start with what was given to us, the 22.5 feet. Remember, we want to, just for your own good, really set things up so there's always sort of a top and bottom, and that way you could clearly know sort of where the units are. And when we do dimensional analysis, as we talked about last time a lot, it's all about opposites cancel. So if you need to get rid of some type of unit, you basically need to put the same unit in the opposite location. This again is why it's really critical to make sure you kind of keep it, units on top, units on the bottom, and you know sort of where they're at. That, like we talked about last time, makes it super simple to really pick the right conversion factor, because I know I want to get rid of feet, so I need to have it in the opposite location. So I definitely should use that conversion factor there. That's going to get me 12 inches on top, 1 foot on the bottom. As we also talked about, it also simplifies the math that you will do when you're doing a calculation with dimensional analysis, because there's pretty much only two types of math operations that you do. Everybody on top, as we talked about, gets multiplied. Everybody on the bottom gets divided. So again, it simplifies, what you should do in terms of the math part of it. By dividing the bottom, that is essentially how those units cancel and why they always need to be opposites of each other. Again, like we talked about, if you divided 2 divided by 2, it gives you 1. If you divide feet divided by feet, it gives you 1. And they essentially cancel out. So here we would, obviously in this particular case, just take 22.5 times 12. And that's going to give us 270 inches in this case. If you are solving for one unit, it should always be by itself and up on top. Again, that will usually give you the right answer. We also talked about the idea of when we're using conversion factors that come from equalities, there are certain ones that are considered exact conversions, which means you do not have to worry about them in terms of your answer. And this would be one of those. That's an exact conversion. Again, exact conversions are pretty much for sure if it's a metric to metric conversion, if it's an English to English conversion. The only time, as we talked about, that you really do have to kind of think about, should I look at the significant figures if you're using a conversion factor, is if you cross over from that metric to English or English to metric, going that, except for obviously that 1 inch is 2.54 centimeters. In this case, that would mean that this is really the only number that we would have to look at in terms of significant figures, and we would have 3 significant figures. The other good thing about dimensional analysis is the only math operations you will ever do in them is multiplying and dividing, which also makes how my answer should look at the end also really easy to figure out, because you always look at significant figures. So because you're only multiplying and dividing, you're always going to look at significant figures. And here we actually need 3. And actually on my calculator, I got 270, and that's only 2, the way it's written. In order to get us to 3, we would, in this case, actually need to put a decimal point in that place. Or obviously, you could also do scientific notation if you wanted to as well. But we would need to actually add that decimal point to make that 0 at the end significant. Any questions on any of that stuff there? All right, so you were working on this problem. So let's go through it here. So If you go to your AM PM and get your 32 fluid ounce drink of Diet Coke, we want to know how many gallons you would have drank. So again, a reminder, as we also talked about, that there are definitely, especially when you're doing conversion problems, there could be more than one pathway you choose to get to your answer, depending on what conversions you choose. Again, if you choose any conversions that are legitimate conversions, then it really shouldn't be an issue. Everybody should end up at the same answer at the end. So one way here, I'm going to use quarts to fluid ounces and quarts to gallons. And my goal is going to go from fluid ounces to quarts, and then take it from quarts to gallons is sort of the pathway I'm going to choose here. Obviously here, those are the conversion factors available to us. So we would start with what was given to us, which is 32 fluid ounces. And as we talked about before, if it helps you just visualize it, you could put it over one. You obviously don't need to put it over one, but if it helps you just kind of keep the top and bottom sort of organized, go for it. Once again here, that's going to help me choose the correct conversion factor. I got fluid ounces on top and I want to get rid of them. So I need the opposite location for fluid ounces, which would be this first conversion factor here. And we would have 1 quart on top and 32 fluid ounces on the bottom. Once again, we'd be multiplying the top, dividing the bottom. At this point, the fluid ounces would cancel. And if I stop the calculation right at this point, I am in units of quarts, which is close to what I want, but I do need to do sort of the second part of the conversion here. As we also talked about last time, if you want to kind of do it in pieces and get an answer, you can. Just try not to round too much, although there's not much rounding here, but try not to round too much if you do get an answer before you continue on. Because I have it set up like this, there is hopefully no guessing that's happening here. I could clearly see my quarts are on top. So once again, opposites cancel. So to get rid of it, I need the conversion where quarts are on the bottom. And in this case, it would be the one here on the right. And we're going to go with 1 gallon is 4 quarts. Again, still multiplying the top, still dividing the bottom. Quarts are going to cancel. I am left with gallons up on top, which is the unit I'm looking for, which is good. We're basically going to take 32 times 1, which you really don't have to multiply it by 1. And we're going to hit equals, divide it by 32, hit equals, divide it by 4. And that gets you 0.25 gallons in this case. I would recommend you doing this, 32. And again, you don't really have to multiply by the ones, but when you do, hit equals. I would recommend to divide by the first number on the bottom, hit equals. Divide by the second number on the bottom, and hit equals. Sometimes a very common error people make is they try to put too much into their calculator at once, and they end up with the wrong answer. So if you want to for sure get the right answer, and you have multiple things to divide by on the bottom, divide by each one individually, hit equals after each time, and you'll always get the right answer if you do it that way. If you're not careful and try to put everything in at once into your calculator, and you don't know how to properly use parentheses, your calculator most likely will do the math wrong, and you will get the wrong answer. So just be careful on that. First off, the answer is 0.25. The answer is not 1 over 4, because that makes me think you're just too lazy to divide the number, yes? So don't leave your answer as a fraction. So always divide it out and get a number decimal, whatever it may be. Do not leave your answer as a fraction. Not terrible in this case, but I've had people go like for the answer in a problem, 453 miles divided by 3,280 hours. Perfect. Not perfect. Yes. So make sure you do divide it, get a number for your answer. In terms of significant figures here, really would default back to this guy, as the other guys are going to be exact numbers. So 2 sig figs there on the back end. Any questions on that one? Okay. Let's take a look then. Actually, let's do Let's skip this one, maybe. Why don't we try this one here? You walk, you're stranded 125 miles away from home. You have no money. You decide, hey, looks like a nice day, a little bit of rain. We're going to walk 55 feet per minute. How many days is it going to take you to get home? So take a few moments there, work it out, see how long you're walking for. See how we're doing. So we are going to be walking 125 miles, sort of a distance or length. We're walking at 55 feet per minute, which is, again, one of those things like we talked about last time, really a conversion factor that's given to you in the problem. It's a rate, which is basically kind of distance over time, right? So kind of distance over time. And this obviously is a distance. And that rate is what's going to allow us to go from really the distance to time. And because it's given to us in the problem, it really is like a conversion factor. And we could use it in the other sort of fashion there by putting minutes on top and feet on the bottom. And again, just choose sort of which one we want to use. One of the problems we do have before we could use that conversion factor is also something we talked about last time. We are in different units of like distance or length, right? This guy's in miles, this one is in feet. As they stand right there, they cannot be used together because those units will not cancel each other out correctly. So you do have an option. You could take the miles and convert them to feet. You could also, if you wanted to, take the feet and convert them to miles. It's your call. I'm going to take the miles and just convert them to feet, and then I could just use kind of the conversion factor the way it is. Obviously, if you did the other way, you have slightly different numbers until the end. So I'm going to go 125 miles. And I'm just going to do a conversion here to take it to feet. This is my equality that I could use to get my conversion factor. And once again, miles are on top. So I know it needs to go in the opposite location. So miles need to go on the bottom. The 5,280 feet need to go on top. Once again, we're multiplying the top, dividing the bottom. Not much here to divide on the bottom there. So 125 times 5,280. Going to give me something like 660, 660,000, I think. That's what I'm maybe trying to spit out there. Feet. Now that I do have it in feet, I'm good to go with my conversion factors because they are also in feet. So I'm just going to take that number here, 660,123. Once again, I'm going to kind of put a 1 underneath it just to make sure I understand feet are on top. That again gives me the easy choice for the proper conversion factor. Feet needs to go in the opposite location. So we got 55 feet per minute. Once again, multiplying the top, dividing the bottom, will get rid of the feet. And right there, by using that conversion factor that was given to us in the problem, we have now gone from sort of distance to time, which ultimately that's what we want, because we ultimately want to know how many days, which, right, is a unit of time. Now what we have at this point is a conversion from minutes to days, right? And once again, we could continue on with our dimensional analysis here, following the opposites cancel. So I want to get rid of minutes. I could use my next equality. Minutes are up on top, which means opposite location is where the minutes need to go. And an hour needs to go on top, still multiplying, still dividing. Minutes now will cancel. If I stop right there, I am now in units of hours. So I'm almost there. I now need to go from hours to days. I think we talked about it last time, only 24 hours, right, in a day, not 60. So once again, having it set up like this, I can clearly see once again here my hours are up on top. So I need to go opposite with the hours and put them on the bottom. And a day goes up on top. Hours will cancel. Once again, still multiplying, still dividing. I am now left with only one unit, which is days. Here I'm going to take my 660,000 And basically everything on top is 1, so you really don't have to multiply by 1. I'm going to divide by the first number on the bottom, which is 55. I'm going to hit equals. I'm going to divide by the next number on the bottom, which is 60, hit equals, and divide by the last number on the bottom, which is 24, and hit equals. And on your calculator, you should have a bunch of 8.3333, just keeps going, pretty much, days. First off, any questions on the setup there? All right, now we need to get to sig figness, right? And make sure that we do end up with the right number of sig figs. Remember, we did start, by the way, with this conversion, right? And with this conversion, how many significant figures should that answer technically have? Actually, should have 3, even though I wrote it with 2, right? Just because I'm not really ending my calculation there. So even though I wrote it with 2 there, it really should have 3 sig figs. This guy here we do need to look at because it's part of the problem conversion factor. That 55.0 is also 3 sig figs. This is exact, so we don't have to worry about it. That's exact, we don't have to worry about it. So really our answer should end up at 3 significant figures, yeah? And we should end up here 8.33 days in that case. Provided you never stopped, it just kept going, that's what I was saying. Any questions on that? So again, you want to make sure you kind of keep track of your significant figures along the way. It may be a case like this where maybe you didn't write the proper number of significant figures on that first number, but technically it should be 3, and you should carry that through. Question? Or no? Did I get your answer? You got it? Yeah. Say it one more time. To get the 8.33? I took the 660,000 number, and everything on top is a 1, so you really don't have to multiply by anything. And then you're going to divide by the first number, the 55, and hit equals. Divide by the next number on the bottom, which is 60, and hit equals. And divide by the last number on the bottom. So you're going to take this number, divide it by this number, and hit equals. Divide it by that number, hit equals. And divide it by that number, and hit equals. Yeah? You're welcome. Other questions? Yeah. Because those would be considered exact numbers because that's a time conversion. So there's definitely exactly, right, 60 minutes and an hour. So that's considered an exact conversion. So you don't have to worry about the significant figures for that. And same thing with the hours. 24 hours in a day is just, there's no more or less, right? So it's exactly that many hours in a day. So it's considered an exact conversion. So you don't have to worry about it. So any conversion that's considered an exact number or conversion, you don't have to worry about the significant figures when you're doing those calculations. And typically that comes from any conversion like time like that, or any conversion that is a metric to metric conversion, or an English to English type conversion. The only conversions you usually have to look at are, like we did here, one that just comes from the problem. It's not like a true conversion, it's just specific for that problem. Or one where you're crossing over from a metric conversion to an English conversion, like 946 milliliters in a quarter, or something like that. You would have to kind of look at that number, stuff like that. Or however many kilograms or in a pound, get the number in that type of conversion, because it crosses over from the different units. Oh, yes. They probably will be provided for you in a table, and you just have to go pick out the right one to use. They probably will not be provided for you in the problem or anything like that, but it'll be probably have a table or something like that that you can pick them out. Yeah. Yeah, so if I was going to punch this into the calculator, I would take the 660000. Because there's really nothing to multiply on top because everything's 1, I'm now going to divide by the bottom. So I would divide by 55, hit equals. Divide by 60, hit equals. And then divide by 24 and hit equal. Yeah. And it should get you the right answer. Other questions? Okay. All right. So the last thing we're going to talk about in chapter 2 here is density. And density of an object is related to the mass and volume of an object. The density of an object determines, for example, whether or not a substance will sink or float, say, in water. Water, for example, liquid water typically has a density of 1 gram per milliliter. And anything that is heavier than that will sink in terms of its density, and anything lighter than that will float. So you can see here a cork has a density of 0.26, which is less than 1, so it floats. A piece of lead is 10.3 grams per milliliter, so it just sinks to the bottom as well. By the way, liquids as well can be separated out by density. If you have liquids together, like in a graduated cylinder, they will separate out based on density. And your most dense liquid would be on the bottom. Your least dense would be on top. If you threw some type of solid object in there and it just kind of floated right about there, that means that that object is more dense than what's above it, but less dense than what's below it, right? So it kind of stops at that particular point. So to calculate the density, it is the mass over the volume. Density typically has 2 units associated with it, grams per milliliter or grams per cubic centimeter. And these are typically the units for density for solids and liquids. We don't really deal too much with it, but gases typically have density of grams per liter, but for the most part, you will come across grams per milliliter or grams per cubic centimeter. A reminder that 1 milliliter is the same as a cubic centimeter. It's a 1-to-1 conversion between it. The number usually stays with the grams part, and it's usually like 1 milliliter or 1 cubic centimeter on the bottom. So number usually just kind of goes with the grams part. Density is mass over volume. That is, D is equal to M divided by V. This is something you could rearrange, and you could solve for volume. Volume would be mass divided by density, or the mass would be volume times the density. Some people like to remember everybody's favorite place, the DMV triangle. Yes. Density is mass divided by volume. Mass is density times volume. Volume is mass divided by density. So that's the way you could kind of remember the formula if you like. Little DMV triangle. Once again, mass is typically in grams to units, and volume's either in milliliters or cubic centimeters. How do we get the volume? There are a couple ways we could get the volume. Very simply, we could take something like a volume reading, right? So as we talked about, you could actually just take a volume reading using something like a graduated cylinder or something like that. If it's a cubic centimeter, maybe it's like a solid cube. You could do those 3 measurements, the length times the width times the height, and that equals a volume. Centimeters times centimeters times centimeters equals a cubic centimeter. So those are 2 very common ways that we can kind of get the volume of a substance. Now, as we talked about, typically speaking, the density of objects are usually a lot more dense in their solid state. And in their solid state, things get pound together a lot tighter to one another. One exception to that is water, as you may be familiar with. Water in its solid state is ice. And when we put ice in our drink, it usually ends up at the top. Ice is actually less dense than liquid water. It's a very unusual characteristic for a substance. Ice is like 0.9 grams per milliliter, and liquid water is like 1 gram per milliliter, so that's why ice floats. What happens when water freezes is the water molecules do not have enough energy to get really close to one another. So what ends up happening is, as they freeze, they create a lot of really open space between the different water molecules. And what that ends up doing in ice is because there's all this extra open space between the water molecules, it increases the volume of it. And if you think about the density equation divided by volume, it makes this number, which makes the density smaller, right? So if you divide small number by larger number, you get a density down in that situation because they can't get as close as to one another as they can. Because they have a little bit more energy, they're actually to one another than they can in the solid state and doesn't create as much open space between them. As I mentioned before, these are typically the units you'll see: grams per cubic centimeter, grams per milliliter. Again, gases are sometimes given in grams per liter. Here's a table from your book of some common density. And I would say for sure you should know, obviously, water's density, liquid water, is 1 gram per milliliter. As you can see here, ice is more like 0.9. So once again, that is why it actually will float. That's also really good if you think about fishes and lakes and stuff, right? Water actually freezes from the top down rather than from the bottom up. That's why the fishes are okay, right? And that's because the cold water, which is ice, floats to the top. Warmer water, which is more dense, goes to the bottom. Top water layer starts to freeze, prevents the rest of the water from freezing. So everybody's good. Super cold under there, but the fishes are still swimming around happy. As opposed to the opposite direction, if it froze from the bottom, that's not so good for the fishes. So that is what happens with your water. Let's skip that. Now, a third very common way that we can find a volume, especially when dealing with what's known as volume by displacement. And volume by displacement means that if you put an object in a liquid like water, it will displace a volume that's equal to its own volume. So if you had a graduated cylinder and you had an initial volume of liquid in it, and you took a solid object and basically dropped it into the graduated cylinder, what's going to happen is when that solid object goes into the cylinder, it is going to cause the liquid level to rise and just be displaced by its own volume, and you will end up with a final volume. If you take the difference between where the liquid level started and where it ended, that is the volume of the object. So typically speaking, the volume of an object is found by taking the final volume minus the initial volume. And that is a very common way when dealing with density that we can find the volume of a solid object. Basically, just pop some water in a graduated cylinder, take a volume reading, drop your thing in there carefully, take another volume reading, subtract the two, and that'll get you what you're looking for. So that's what you can kind of see here before they put the object in, after they put the object in. If you take the difference between those two volume readings, it will give you the volume of its object. And that is, when you're calculating something like density, a very common way to figure out the density of the object. Now, if it's a solid object, you want the mass, you could just take it to the balance like it shows in the picture and just weigh it, right? So you can put it up there, get the mass of it. And now you'll have the mass from weighing it, you'll have the volume from displacement, and you can put it together. So if you use the numbers in this example, the mass of zinc that they weighed out there on the balance was 68.6 grams. The initial volume of the liquid in the graduated cylinder was 35.5. The final volume after they put the solid in there went to 45. When you subtract that, you get the actual volume of the object. So that 9.5 milliliters in this example would represent the volume of the zinc metal they put into that graduated cylinder. Now we could calculate our density by taking the mass divided by the volume. We do have to look at significant figures here. Here we are subtracting, right? Which means we are looking at decimal places, right? So there we are subtracting. We're looking at decimal places. They each have one decimal place, which means our answer when we subtract should have one decimal place, but it still has two significant figures at 9.5. That's important because the very last calculation we're doing is dividing, right? So we're going to divide those numbers, and we're looking at significant figures in that case. That is 4 significant figures divided by 2. That is why our answer ends up at 2 significant figures. It is actually based off of the volume calculation is really what determines that. Any questions on that there? Yeah. Yeah. It's a little bit different. So the idea here is you would probably put an object in there. Obviously, that would sink, basically, right? It's gonna, let's say you solve it on the liquid water. Yeah. If water is the liquid you choose to use. Yeah. Other questions? Yeah. All right. So why don't you try this one? What is the density of 48 grams of a metal if the graduated cylinder rises from 25 milliliters to 33 milliliters? After practice in chemistry is to kind of pull out the information from the problem and sort of label what it is. And a lot of times that will kind of point you maybe in the right direction if you're not sure what you should be doing. So obviously 48 grams is a mass. So we have a mass of 48 grams. We have water in a graduated cylinder, which is an initial volume of 25 milliliters. We're going to take that solid and put it in there, and that's going to give us another volume, which is a final volume after we add the metal, which is 33 milliliters. So remember that to find the volume of the object, which is what we're looking for, we basically want the difference in those volumes, if I could draw a straight line, the difference between those two. And that's where we would want to start in this calculation because we definitely have mass, we have volume, and that's going to allow us to get to density in this case. So the volume of the object in this case is always going to be final volume minus initial. So our final volume here is 33.0 milliliters minus our initial 25.0 milliliters. That's going to give us 8.0 milliliters. Remember here we are subtracting. We are not looking at significant figures. We are looking at decimal places, right? So 1 decimal place for each. That answer should technically have 1 decimal place. Although it has 1 decimal place, it has how many significant figures? It does have 2, which is going to be important for the next part of the calculation, right? Because now we're going to actually do the density calculation. We're going to take the mass, which is 48.0 grams. We're going to divide it by our volume we just calculated, which is 8 milliliters. So we'll take our 48 divided by 8. And that is going to give us 6. By the way, the units here do not cancel. So the number always stays with the grams part, and it's always per 1 milliliter. Did I remember sig figs though? I did not, right? Because we do need to look at our last calculation part. This guy has 3 sig figs, right? This one has 2 sig figs, which means I actually need to put a 0 in this case, right? To get to the proper number of significant figures. Yeah. Any questions out there? So once again, you do have to kind of, like we talked about last time, it's important to keep track of your sig figs through your calculations. And then sort of the last calculation kind of helps you determine maybe where you should end up. But it can be a previous calculation that determines where you actually end up. Any questions on that there? Okay. They agree. That's good. So let's talk about using density itself. Density can be used as a conversion factor. So let's just say, for example, we had our density we just finished getting there, 6 grams per milliliter. We could always use density as a conversion factor if it's given to us. And we could flip it around and put the milliliters on top and the grams on the bottom. And we could actually use it as a conversion factor. And the nice thing about it as well is, frankly, if you have a problem where you have density given to you, and maybe you have a mass given to you, maybe you have a volume given to you, and you need to solve for either a mass or a volume depending on what's given to you, you actually do not even have to worry about the formula or rearranging the formula. You could just do a dimensional analysis approach with the density as a conversion factor, and it will rearrange that equation for you without you even having to worry about it. So let's just say, for example, I had 52 grams of a solid with that density of 6 grams per milliliter, and I want to know what is the volume, right? Now, clearly I can take the D equals M over V and rearrange it and then put my density, since I know two of the three things, right? I have my density, I have my mass. I could rearrange and solve for volume. Now, maybe you don't remember the formula, or maybe you're afraid you'll mess it up rearranging it. So the good approach you could do here is actually just take a dimensional analysis approach. And that is, you could use this density value as a conversion factor, like I have written here. So I'm not even going to worry about the equation. I'm not even going to worry about, should I be dividing, should I be multiplying. I'm just going to think of this as a dimensional analysis problem, which means I have grams and I want volume. And unit of volume is milliliters. So I need to end up in milliliters. I got grams to start with. So I'm going to go 52.0 grams, just like I'm doing a traditional dimensional analysis problem. I'm even going to throw a 1 over it, just like normal. And now what I know with dimensional analysis is, if I want to get rid of my grams, where do they need to end up, on top or bottom? Bottom. So now I could go to my density value, which is a conversion factor, and go, all right, I probably should use that one, which is grams on the bottom, right? And I'm just going to do it like normal, 6 grams and milliliters. Because I know I'm doing dimensional analysis, I already know what math I should be doing, right? Everything on top should be what? Multiplied. Everybody on the bottom should be divided. Now I just divide that. Grams go away. I take 52 divided by 6. That gets me 8.667 milliliters. Now I could do my significant figure still. That is 3 sig figs. That is 2 sig figs, which means my answer should actually end up at 2 significant figures and 8.7 milliliters. Now, I just did my density formula without even touching the formula, right? Because if you take this formula and rearrange it, volume is mass divided by density. That is mass, that is density. I just did that without even thinking about the formula, thinking about, hey, should I rearrange it correctly? Should I multiply? Should I divide? So I highly recommend, if you have a situation like this, take the dimensional analysis approach, because you don't have to worry about the formula, don't have to worry about remembering the formula. Just need to know what units you need to get rid of and which ones you need to end up with. Yeah. Yeah, so on the other one, we really didn't have an opportunity to do that. In the case of density, given the density like we were in this particular problem, then you could use that as a conversion factor. In the previous one, we only had the mass, right? And we only had the volume. So we didn't have really a conversion factor, because a conversion factor is really a fraction. So you need 2 units. So here, when you do have density, you have both units that you could use as a conversion factor. And that's why you can really do it on the other one. Yeah. Because we're multiplying and dividing, right? And then we look at the smallest number of significant figures. So 52.0 is 3 sig figs. And this 6.0 is 2 sig figs. I'm sorry, 2 sig figs for the 6.0. 52.0 is 3 sig figs. So 2 sig figs. The least always, yeah. Yeah. Other questions? So dimensional analysis is really helpful. Like I said earlier, a lot of times you may not If you could just figure out and you have something that you could use as a conversion factor, it will actually rearrange the formula for you. And if you just remember how to do dimensional analysis, you know math-wise what you need to do, multiply or divide. Any questions on that there? So why don't you give this one a go? Unknown liquid has a density of 1.32 grams per milliliter. What is the volume of 14.7 grams of a liquid? Okay, so let's take a look. Once again, obviously we're dealing with density, so it might be helpful to whip out the formula there. We have a density given to us, 1.32. Again, density has 2 units, so you might want to write it like a conversion factor. And we obviously have the density there. We're looking for the volume. So we're looking for this guy. And obviously here we have a mass that is 14.7 grams. So we do have a mass. So clearly, just like last time, if you wanted to, you could rearrange this equation, mass over density. But once again, since you do have the density given to you, which again can be used as a conversion factor, you may just want to take that dimensional analysis approach, and you could flip this around and use it like such. So if I take my mass, which was again 14.7 grams, taking the dimensional analysis approach, grams are on top, gonna need to use it in the opposite location. And now I pretty much have just rearranged the density equation without even really thinking about the density equation. I basically just did that over here by just taking the dimensional analysis approach to it. And I know in dimensional analysis, multiply top, divide the bottom, grams cancel, gets us 14.7 divided by 1.32, and we're going to end up with an 11.1 milliliters in this case. Sig fig wise, 3 sig figs there, and also 3 sig figs there as well. Once again, obviously, if you just plugged and chugged into the equation, should get the same answer. Yeah, but you don't have to worry about the equation. You could kind of take that approach, and it might be helpful. Question on density. Yeah. So you need to be able to solve for obviously density, mass, volume. You need to be able to do volume by displacement. Any questions? All right, that actually is going to wrap up chapter 2. The last part of chapter 2 about specific gravity we're not going to worry about, so don't worry about that. Okay, we're going to get started up again here. Again, a reminder that chapter 3 has been up there for a bit, so make sure that you watch it. We are going to go to chapter 4 here, which will be the last chapter that will be on our first exam. We're going to talk about the atom in here. We're going to talk some properties of the atom. And we're going to talk about electron configuration, I think, in this chapter as well. So we're going to start with talking a little bit about elements. Elements obviously can be found on the periodic table. A couple of reminders, some terminology that we may come across here. Obviously, elements are really the basic units of everything. They're made up, obviously, of atoms, which represent the different elements. When we have 2 or more atoms together, that is what is known as a molecule. Now, when we have 2 or more atoms of different elements, that is a compound. So there is a difference between a molecule and a compound. A molecule, in order for something to be a molecule, you really just need a basic definition of 2 or more atoms together. Now, those 2 atoms could be the same element. They could be different elements. But that's really just how you can think of it like a basic definition. In order for it to meet sort of it being a molecule, all I need is 2 or more atoms, 2 the same, 2 different, or more. That would be it. Now, for a compound, though, there is a restriction on that 2 or more. It does have to be 2 or more elements involved for it to be a compound. So not all molecules are compounds, but all compounds are molecules, actually. So that is how that works. So to maybe further complicate things, sometimes elements are molecules. So, for example, there are like a list of certain elements that how they naturally come is they come as molecules. So that is H2 hydrogen, oxygen, nitrogen, chlorine, fluorine, bromine, and iodide. Every single one of those are elements. And they're elements because they are made up of only atoms of the same element. So if you have hydrogen, which is how hydrogen naturally comes, it comes as two hydrogen atoms together. Because they are both hydrogen, that makes it the same element and is considered an element. This is also considered what is known as a diatomic molecule. It is also a molecule because it is made up of two hydrogen atoms, which means it meets the definition of a molecule. H2 or any of those up there do not meet the definition of a compound because in hydrogen, you only have hydrogen atoms involved. Now, if you had what we saw earlier, which was H2O, that is water, that is made up of three atoms together, two hydrogen atoms and one oxygen atom, which means it meets the definition of a molecule because it's two or more. It also is two or more elements involved. It's hydrogen and oxygen, which means water is also considered a compound. Water is not considered an element because it has two different elements involved. It has hydrogen and oxygen. So that is some important differences. Since we're talking about elements, those 7 elements, that again is how they naturally come when they are not combined with anybody else. Basically as twos. Everybody else on the periodic table, they come when they're not by themselves. They come when they're by themselves as ones. They don't come as twos. So these are the only elements that come as twos. And for the most part, most of those 7 are gases. Hydrogen gas, oxygen gas, nitrogen gas, fluorine and chlorine. Those are all gases. Bromine is kind of like a gas with a little bit of liquid, and iodine is a little bit different, but most of those are in the gas state, and that's just naturally how they come. So if you have hydrogen by itself, by the way, it comes as H2. You'll never just have like one hydrogen by itself or anything like that. If it is just molecular hydrogen or hydrogen gas, it should always come as twos. Any questions on that there? Okay. Now let's talk a little bit about elements and their symbols. We use symbols to represent elements. Symbols can be basically one of two ways that they're written. They're either written as a 1-letter symbol or a 2-letter symbol. If it is a 1-letter symbol, we always capitalize it. So capital K is potassium. Capital C is carbon. If it is a 2-letter symbol, we always capitalize the first letter, but never the second. So Al, capital A, lowercase l, aluminum. You never should capitalize both letters because, for example, if you write capital C, capital O, you may be thinking you're writing cobalt, but you are not. You're actually writing carbon monoxide, which is very, very different than cobalt. So if you are writing a symbol, you should never capitalize both letters because you may be actually saying something that you don't mean to be saying when you do that. So if you're somebody that writes in all capitals, don't do it for symbols. Yes, so just the first one. Second one, no capitalization. Elements are pure substances. They are essentially as far back as you could go. So a compound, for example, you could break up into elements, but you can't go any further than elements. You could think of the elements as kind of like the alphabet, right? There's only 26 letters, I think, still. Maybe a bunch of different words you can make, right? Depending on what combination of those letters you put together and how you put them together. It's kind of the same idea with elements, depending on what you put together, how many of what you put together You can make all kinds of different compounds and substances from them. Um, Here are some of the symbols and the elements that go with it. Should you know these? The answer is you probably should start becoming familiar with the symbols and the names that go with them. As the next chapter we will talk about, we will start talking about naming things. That has all kinds of rules involved in naming. So you don't want to be still trying to figure out, what does that symbol sort of represent? So, the quicker you kind of get a handle on the symbol and the names, it will make that next chapter a lot easier because you could just focus on how to apply the naming part of it rather than trying to figure it out. So what on the periodic table should you worry about? I know, everything. No, I'm just kidding. Most everything. Definitely to the left, definitely to the right and up, we see a lot. I would say kind of in this section we see a lot, and kind of down right about there we see a lot. We don't really do too much with the bottom rows. Not a heck of a lot like in this area and stuff like that, but definitely left, right, upper right, kind of curving down where the staircase is. Those symbols and elements do pop up a lot along the way, but definitely not too much on the bottom and things like that. Now, sometimes the symbols may seem weird to you, and they do come from a wide variety of sources, historical names, named after scientists, Latin names, Greek names, and so forth. There, as I mentioned before, if you want to do cobalt, you should do capital C, lowercase o. And again, CO is something very, very different. Again, here's some of the other symbols. I would say a couple of ones that sometimes people have a hard time with. Mercury is Hg, yeah. Gold is Au. Silver is Ag. Copper is Cu. Iron is Fe. Potassium is K. Se is selenium, my favorite, everybody should have a favorite element, I suppose. Sn is tin. Sb is antimony. Pb is lead. So most of them you could probably get from the name. Obviously, sodium is Na, right? So that's a little bit different than sodium sort of name. So like I said before, the answer to maybe a question you may have is yes, you sort of need to know the elements and the symbols, and it definitely will be very helpful as we go into the next chapter and beyond as well. I probably won't give you anything that maybe we haven't talked too much about, but you should have definitely some familiarity with it. You will not get the names on the periodic table. You will just have the symbols. Yeah, so periodic table will only have the symbols, so you kind of need to have some recognition of those guys. All right, and then here's obviously from your book, the table continuing on. Some of these ones we just talked about. Again, gold comes from Rem, which is why it's Au. Silver there, Ag. All right, so let's run through some of these. Iodine is I, is the symbol. Iron is Fe, again, capital F, lowercase e. Magnesium is Mg. Zinc is Zn. And lithium is Li. Again, two-letter symbols, capital, lowercase, one letter, capital. Now, if we have some of this, P is phosphorus. Ar is argon. Mn is manganese, not to be confused with magnesium we just did. So that is right there, number 25. Be is beryllium, and K is potassium. So again, this will be super helpful to you as we get into that naming chapter, not having to kind of pause and try to figure out, what elements, what. You could, again, like I said before, just kind of focus in on the rules you have to follow when you name things, and it'll be very helpful along the way. Yeah. Yeah, so technically it's in chapter 4, so there might be a couple of questions on, some, the symbol for the element or something like that. Probably in most cases, outside of maybe chapter 4, this first exam, this and more like naming and stuff like that is sort of how you'll incorporate it. Yeah. But you definitely are responsible, and you may have a question that says, what is the symbol? The symbol Na represents, sodium or something like that. Questions. Right now, didn't say doesn't worry about any of that, but hopefully before we take the exam, there'll be some questions on it. All right, so let's talk a little bit about the atom itself. The atom is really the basic representation of any element. As you may know, we'll talk a little bit about it. The atom really has three parts. There are protons, which are positively charged. There are electrons, which are negatively charged. And there are neutrons, which have no charge. And we're going to talk a little bit, not great detail here, but we're going to talk about some experiments and sort of what led to some of the understanding of these sort of particles within the atom. These are sometimes referred to as subatomic particles. And atoms are extremely small, but they still have this internal structure, which again are made up of these protons, electrons, and neutrons. So let's talk a little about some of that stuff. Atoms of a particular element will all be like aluminum atoms here, for example. And again, they have similar characteristics because they're all the same element along the way. Now, one of the earliest sort of ideas and theories about the atom was one that was brought by John Dalton. He was an interesting guy. He liked to go bowling on Thursdays. Hey, you never know when that might show up on an exam. But he did come up with what's referred to as Dalton's atomic theory. Now, if you remember, we talked a little bit about theories early on. And remember that theories are not always correct in all aspects. They could be maybe revised. They could be based on later research, determined maybe not so correct. And actually the same thing happened with Dalton's atomic theory. But let's go through the points of it, and we'll talk about sort of what things are maybe not so correct. He said that all matter is made up of these tiny particles, which are atoms. He said that all atoms of a given element are identical to one another, and atoms of different elements are different from one another. Now, this is one of the things where Dalton's atomic theory is sort of incorrect, and it's this part of it that all atoms of a given element are identical to each other. And that does not hold true because of the existence that was found of things known as isotopes. And isotopes are the same element, but they have different masses. So obviously, if they are the same element, but they have different masses, they are not identical to each other, right? So if you have two isotopes of copper, and they have different masses, those atoms are not identical to each other. Otherwise, they would have the same mass. So there is something different. And as we'll talk about, what is actually different is, in isotopes, the number of neutrons. So the number of neutrons in those isotopes is actually different. And that is what gives them that different characteristic of different masses. Atoms of two or more different elements combined to make compounds. So as we talked about, that is still good. A particular compound is always made up of the same kinds of atoms and the same numbers of each kind. That is true. So if you have water here, water in Europe, you buy water anywhere. Ultimately, the fundamental part of that is water, which is H2O no matter where you go, 2 hydrogens and 1 oxygen. May cost you more depending on where you buy, I suppose, but ultimately it is still H2O, right? So that is true. He also said that a chemical reaction only involves the rearrangement and separation of the atoms, and they recombine in a chemical reaction. And that is true as well. So in chemical reactions, the only thing that happens, as we'll talk about in some later chapters, is everything we start with all they do is just break away their bonds, and then they kind of reassemble on the other side and make new substances. That only involves really electrons, and that means that in a chemical reaction, we have a conservation of the elements. So if we started with 4 carbons at the beginning of the reaction, we will end with 4 carbons on the end of the reaction. They may just be in different things, but we will still have the same 4 carbons we started with. We won't create any new elements. We won't lose any elements along the way. And in a chemical reaction, that is always the case. The other part of Dalton's atomic theory, which is actually incorrect, has to do a little bit with that idea. It's the idea that atoms are indivisible. You can't really kind of break them apart into something else. And you actually can in nuclear reactions, which we don't talk about in this class. We skip that chapter. But in nuclear reactions, all you do is take one atom of an element and change it into a different element. So you actually can do that. But in normal chemical reactions that we talk about in this class, the only thing that happens is we break bonds, keep the elements the same all the way through the chemical reaction. Everybody just rearranges. Any questions on that? All right, so as I mentioned before, atoms were believed to have some type of internal structure, even though they're really small. Again, protons, electrons, and neutrons are these subatomic particles. And one really important concept in chemistry that pops up in a lot of places is really this idea. It is what is sometimes referred to as electrostatic attraction. The idea here is, much like in life, if you have 2 positive people, they definitely don't want to be near each other. That's just too much positively. They're going to repel one another. You got 2 negative people, that's probably not a great situation either. They're going to also want to not be near each other, I imagine. So, they always say find somebody that balances you out. So, much like in life, in chemistry, things that have opposite charges are always attracted to each other. So something with a positive charge will always be attracted to somebody with a negative charge, and they will be attracted to one another. Actually, the attraction that occurs is based on how big those charges are. So if you have something that has like a +4 charge and a -4 charge, they're going to be a lot stronger attracted to each other than somebody with a +1 and a -1, but they both will still be attracted to each other. So if you ever come across something, for example, in like chemistry, where you have 2 negative things near each other, they're going to try to get as far away as possible from one another. 2 positive things are going to try to get away as far as possible. But positive and negative things, that is good. They're going to want to kind of come together. As we'll talk about in the bonding chapter, that is the basis of what is known as an ionic bond. A positively charged guy and a negatively charged guy come together to make an ionic compound. So they are attracted to one another. Any questions on that? Now, this sort of attraction and repulsion was very helpful in experiments that were performed to understand the atom, because they could use something like a magnetic field and a electrical field, and they could use particles that had charges. So a lot of experiments that were done to sort of understand the atom were done using radioactive particles like alpha particles. Alpha particles have the alpha symbol, and they were positively charged radioactive particles. They also sometimes would use beta particles. Beta particles with the beta symbol are negatively charged particles, and they would sometimes use gamma rays. Gamma rays are pure energy. They actually have no charge. That's the symbol for gamma sometimes. As you might notice, that's very similar to the particles found in an atom. Protons that are positively charged, electrons that are negatively charged, and neutrons have no charge. So using these sort of radioactive particles and things like electrical fields and magnetic fields, they were really able to explore sort of the structure of the atom. So for example, if you had an electrical which basically had a positive side and a negative side, and you shot a particle through it, and those particles bended upwards towards the positive side of the electrical field, what would you guess the charge of those particles would be? Negative. Opposites attract, right? So it's going to bend towards that positive side, right? It's definitely going to go away from the negative side. And if you shot some particles and it bent towards that negative side, that probably meant those particles are positively charged. And if you actually shot particles and it just went straight through, they probably had, no charge, right? 'Cause they're not affected by the electrical field. A magnetic field works the same way, has a north pole, south pole, kind of the same deal. It'll kind of bend those things. So a lot of those things were used to understand sort of the nature of an atom and then when they were investigating the atom. And probably the first thing that was investigated was actually electrons. And the development of the cathode ray tube allowed the cathode ray tube. Maybe you have a TV at home. Seen a TV at home? The old type TVs used to be like on the ground, not hanging on the wall. They had a back. You open it up, call the TV repairman to fix your TV instead of going to Costco and buy a new one, right? Those had cathode ray tubes in it. Old computer monitors, not like that one. That has like big backs. Have you ever seen one of those older ones that had like the big back in there? That has a cathode ray tube in it. They used to be called CRT monitors for cathode ray tubes. And basically what a cathode ray tube is, it is a tube that has a negative side and it has a positive side. And it would shoot a beam of basically negatively charged electrons. And because these electrons are negatively charged, it would move away from the negative side and obviously be attracted to the positive side. They would actually put a little fluorescent material at the end. You could actually see where the beam is actually hitting. It would kind of light up and stuff like that. So by using the cathode ray tube, Thomson was able to figure out the charge to mass of an electron. It was followed up by another experiment by a guy named Milligan, who was able to figure out the charge of an electron. It's a really big kind of 1-2 experiment combination that led to basically the mass of an electron. And the mass of an electron is roughly in grams, 9.09 times 10 to the minus 28 grams. That is a large number or a really small number? A really small number is like 28 places to the left and down a bunch of zeros, right? So it makes it really, really small. And that was a major sort of outcome of it, and really some good understanding of the electron and some of its properties. That understanding and those experiments led to an early model of the atom, which is what we see on the bottom. And the early model of the atom was also made by a guy named Thomson, and it is referred to as a plum pudding model. And the idea is, as you see in that picture, they thought the atom definitely contained electrons from the results of these experiments, which they knew were negatively charged. But they also always thought that the atom was neutral, which means if they have negatively charged electrons, the atom has to have something that is positively charged to balance it out, right? So if you're neutral, all your positives and all your negatives equals zero, right? Everything balances out to zero. So the idea that they had was the atom is the sphere, and within the sphere is all this positive charge spread out all over. So the positive charge is just kind of spread out all over the circle. And embedded inside, as you can see in the much better picture to the left there, are these negatively charged electrons. And they felt that most of the mass of the atom was actually made up of these electrons. The reason they call it plum pudding, because that's a dessert of pudding and raisins. And they thought, well, the pudding is probably like the positive part of it. The raisins kind of in it is the electrons. And that's what they thought the atom looked like. And this was sort of the accepted model of the atom until more experiments were done. And probably the major experiment that really truly helped us understand what truly the atom looked like was the experiment that was done by Rutherford. And Rutherford did what is referred to as the gold foil experiment. And what he did was, as the picture shows, he took pieces of gold foil and other metals, and he shot at it alpha particles, as we were just talking about. Those are those radioactive, positively charged particles. And what they expected to happen and what actually happened were actually two different things. So what they expected to happen based off of this model of the atom was we have all this positive charge that's really spread out. So what they anticipated would happen when they shot these alpha particles, which are also positively charged, heavy, they're moving really fast, they thought it would be able to punch through all that positiveness, but there would be some deflection as it kind of went through. So if you think about it like a piece of paper, right? I don't drop everything. If I hold this paper really tight on one side and on the other side, and I had a pen or something that was shot at it really hard and fast, I'd probably be able to punch through that paper, right? But there would be some deflection, right, as it kind of punched through there, if this was really, spread out all over. And that's really what they thought would happen when they did this experiment. What they actually saw was when they shot the alpha particles at the pieces of gold foil, most of them just sailed right through, no problem. So it just moved straight on through. But what they were able to witness, though, is every so often they would see these alpha particles bounce off at these really big angles. And sometimes the alpha particle would head back to where it came from. And that was really surprising to them. So what that meant was maybe this plum pudding model here is maybe not so correct. They had to sort of move away from it. And they had to think about what they observed in their experiment. And if you just think about it logically, if I have alpha particles that go straight through, no deflection, what did they hit? They didn't hit anything. Like if I took my pen and threw it that way, right? It's not going to have a problem. There's nothing in its way, right? It's just going to sail right through, no problem. Now, because alpha particles are super positively charged and heavy, in order to make a positively charged particle bounce off at these really large angles, what by chance does it have to hit? Something that is what type of charge? If it was negative, opposites attract, right? It's just going to stop, right? Because it's going to be attracted. So it can't be negative. It has to be positive, right? Same charge repels, right? So when it bounces off at these really large angles, it had to hit something that was super duper, those are scientific words, positively charged to make it bounce off at these really big angles. So what they had to do was kind of throw away the plum pudding model and go, well, maybe my positive charge is really not spread out all over the atom, but if I took my positive charge and I folded it, what do they say? How many times can you fold the thing before you can't go anymore? And instead of my positive charge being all spread out, all concentrated in one area, if I were to shoot my pen at it now, it's going to definitely bounce off, right? I won't do it with this pen. Last time I did it, it flew in the first row. It's not too good. But so this was a really big experiment that helped us understand the idea that the early model, not so correct. And basically, they had to come up with this idea that the atom is mostly empty space. So the atom itself is mostly empty space. It has a positive core, which is known as the nucleus. And inside the nucleus, that is where we find protons, which are positively charged. And later on in like 1930s, they discovered neutrons are also in there. So inside our nucleus are protons and neutrons. Our electrons, which are negatively charged, are actually out in that open space, that empty space. They're flying around in the empty space. Just so you know, electrons do not travel in pretty little circles, yeah? They travel randomly about the nucleus. Don't really know how they're traveling, don't know where they're at. I know sometimes biology likes pretty little circles for electrons, but they don't really travel that way. They travel in a pretty random fashion. By the way, should there be some type of attraction between the electrons and the nucleus, which is ultimately positively charged? There is. That's why those electrons just don't fly away, right? There's this attraction to the nucleus for those electrons that are flying around that ties them to that nucleus and that atom. Also, why, as we'll talk about, there are certain electrons which are further away from the nucleus that can be removed and involved in bonding, but electrons closer to the nucleus are really held tightly because they're very close to that positive charge, very hard to remove. The other major sort of difference was most of the mass of the atom is actually the nucleus and not the electrons. So most of the mass of the atom is the nucleus. And again, not the electrons. So this is the modern version of the atom. In the nucleus, protons, neutrons. Electrons travel around randomly about in the empty space. Most of the mass of the atom is the nucleus. Any questions on that there? All right. In terms of masses of protons, electrons, and neutrons, your book uses AMU, and AMU is an atomic mass unit. It is a unit of weight. And you can see a proton has an AMU of 1.007. A neutron has a mass of 1.008 AMU. And you can see our electron, 0.00055 AMU. Essentially, a proton or a neutron is about 1,800 times heavier than any electron. So the electron is the least massive of all three of those subatomic particles. It is the lightest particle. Believe it or not, the heaviest is the neutron. It just barely beats out the proton. It's very, very close to each other. If you go about 3 decimal places, the neutron beats it, but they're super close to each other. But in order, neutrons are the heaviest, protons are pretty much right next to them, and then electrons are way, way lighter particles. This also reinforces the idea that came out of Rutherford's experiment of most of the mass of the atom is the nucleus, because in the nucleus, you have protons, which are 1,800 or so times heavier than an electron. You have neutrons, which are 1,800 times heavier than an electron. So the nucleus is where you find the heaviest particles in an atom. Electrons are the lightest, and most of the mass of it is that nucleus. Any questions on that? And here's a table from your book that explains that and where we find these guys. You could think of an atom as like a football stadium, since we just had the Super Bowl. I don't know who, probably the Rams. I don't know. They were at home. Too soon. I know. It's okay. It'll be next year. But you can think of the atom as like a football stadium, and like the nucleus is like a marble on the 50-yard line in the middle. Yeah. So mostly empty. Very small volume is actually the nucleus, but it's actually the most massive part of the atom is that little spot there. But there's a lot of empty place for a lot of electrons. You don't understand football? Well, think of a big room like this room, right? The atom, marble in the middle of the room is the nucleus. Yeah. Other questions? All right. All right. So which of the following subatomic particles meet these descriptions? The one that's found outside the nucleus is, yep. The one that has positive charge, no charge. Sounds good. I like it. All right. True or false? The mass of an electron is greater than a proton. False. It's the lightest, right? Protons have positive charge. Electrons have negative. Yep. Nucleus of an atom contains only protons and neutrons. Correct. Yep. And here's that picture. Again, you can see nucleus, small part, big empty space. By the way, the different color there, sometimes referred to as an electron density map. The darker color blue is a place where there's a higher probability of finding an electron. As you can see, as you kind of go away from the nucleus, that blue color gets lighter, which means there's a lower probability of finding an electron. Doesn't mean you can't find one out there, but it's just a smaller opportunity to do so. All right, any questions on the atom? You know the structure and makeup of an atom? All right. Let's talk about some more properties of atoms. That's atomic number, mass number, and isotope. The chemistry of atoms comes from its electrons. As I mentioned before, in a chemical reaction, that is really the only thing that's involved is electrons. And if you think about the structure of the atom we just talked about, electrons are on the outside, which means when two atoms come together, electrons are the first things that kind of come in contact with each other. So they're involved in chemical reactions. The properties and differences of atoms when they do bond are a result of these electrons kind of coming in contact with each other. The first type of number we're going to talk about is the atomic number. The atomic number is sometimes abbreviated with a Z to represent the atomic number. The definition of the atomic number is the number of protons there are in an atom. Now, if you look at the periodic table, you will see a symbol, and above the symbol, you typically will see a number on the periodic table. That is your atomic number. Now, the atomic number, which is the number of protons, will also tell you the number of electrons. So if you think about what we just talked about, there's only 3 particles in an atom: protons that are positive, electrons that are negative, and neutrons have no charge. So if something has to be neutral, the number of positive charges, which are protons, has to be balanced by the same number of electrons. So if something is neutral, the number of protons and electrons will be the same number. It is important to remember, though, if you are asked the question, what is the definition of atomic number? The definition is only protons, nothing to do with electrons. So the definition of atomic number is how many protons there are. The second thing it will tell you as a side note is if it is neutral, it'll also tell you how many electrons it has to balance it out. By the way, when you look at the periodic table here, all the numbers that we see up on top are the atomic numbers. Do any of these numbers repeat up on top? They do not. They're all different. That means that each element has its own unique atomic number. And that means it has a different number of protons for each. That means when we think about our 3 protons, electrons, and which one is the most important in terms of what element? It is protons, which is the atomic number. The number of protons tell you what element you're dealing with. So if I have, like it says there, nitrogen, and I go to the periodic table and I find N, which is nitrogen, I will see lucky number on top. That means it has 7 protons, which are positively charged. And if this was a neutral nitrogen, it will have 7 electrons, 7 positives, 7 negatives, give you no charge overall, right? It equals 0. Will I ever have a nitrogen atom that has 6 protons? I will not, because number 6 on the periodic table is carbon. Yeah, and that would be carbon, right? So that is why, by the way, when we do a chemical reaction and it only involves electrons, we never touch what's in the nucleus. That is why we never change the elements. We don't lose elements, because in a chemical reaction, the only thing involved are electrons. We never touch the protons. They stay the same. And that is why when we start with 4 carbons in a reaction, we still have 4 carbons at the end, because we never touched or changed the protons. And that's also why in nuclear chemistry, it always changes, because in nuclear reactions, you do nothing but change protons to neutrons, neutrons to protons, and that's what changes the elements. But in chemical reactions like we deal with, it only involves electrons, never touches in protons. Elements stay the same throughout the reaction because of that reason. Any questions on that there? Yeah. Well, we'll actually talk about that in the bonding chapter, which is coming up next. But it has a little bit more to do with the electrons and what it's trying to achieve through bonding. And in a sense, everybody, when they're bonding, they all want to achieve the same electron configuration as everybody here in this column of the periodic table. And that's really more, why they kind of do that. All right, so the mass number is another number which is sometimes abbreviated with an A. The mass number is the number of protons and neutrons in an atom. So if we have our mass number, which is number of protons plus the number of neutrons, and we have our atomic number, which is our number of protons, we could actually use those two together, and if we subtract, protons go away, and that will tell you how many neutrons there are. So if you take the mass number minus the atomic number, that will tell you how many neutrons there are in that particular atom. Now, when you calculate the mass number, the atomic number, how many protons, electrons, and neutrons there are, they all have to be positive whole numbers. And that's something to really keep in mind. So when we go to the periodic table and we look at hydrogen, there's a 1 up on top, which is our atomic number. If we look on the bottom, we'll say 1.008. Is that my mass number? The answer is no, it is not your mass number. First off, that is the atomic mass. It is not the mass number. And that is, for an easy way to remember that, is when you do the mass number, atomic number, protons, electron, neutrons, they all have to be what type of number? A whole number, right? If you look at the periodic table, all these numbers, they're pretty much decimals. They're not whole numbers, right? So that is not the mass number, although it is often put on people's exam as the mass number, because what happens is people think, my mass number is kind of similar to that number. They probably just rounded. They did not just round, by the way, yes? So don't write the bottom number there. It is not the mass number. You will be given enough information in these type of problems to be able to calculate the mass number. You'll know the number of neutrons given to you. You'll know the protons, or you'll be given the mass number. But very commonly, again, people get that confused because a lot of times the mass number is very similar to that bottom number, and people just think they rounded it off or something. It is not that number, so don't use that number. Use what the numbers are in the problem to figure out mass number and number of protons. Any questions on that? We'll actually later in this chapter talk about atomic mass and obviously what it is. We talked about isotopes a little bit earlier. And isotopes, as I mentioned before, are the same element, but they have different masses. And the reason they have different masses is they have different numbers of neutrons. So these are three isotopes of the element hydrogen. There's hydrogen, there's deuterium, which is heavy hydrogen, and there's tritium, which is like the radioactive version of hydrogen, basically. Now, every single element will have protons, electrons, and neutrons. The only element that does not have neutrons is hydrogen. Hydrogen is weird and unique in a lot of ways. Hydrogen only has an electron. It does not have a neutron. Everybody else will have all three, but hydrogen only has those two, protons and electrons. This is the way that we sometimes will write our symbol there. We will use the symbol. Up on top left will be the mass number. Bottom left will be the atomic number. So let's take a look at each of these. I go and I see hydrogen, and I see it has 1 proton. If I wasn't sure how many protons it has, I could go to the periodic table and find its number, which is number 1. And I know the symbol for hydrogen is H. Its atomic number, which is this number, would go bottom left. Its mass number is protons plus neutrons, which would be 1 plus 0 is 1. And that would be the isotope symbol for hydrogen. Again, the top number is the mass number. And the bottom number, which is the atomic number, the number of protons. By the way, if you take the top number minus the bottom number, that gives you the number of neutrons, right? 1 minus 1 is 0. Yeah, so that gives you the number of neutrons. Now you come to this guy and go, deuterium, maybe even cross it out like I did there. You go deuterium and go, I don't know what element that is. You should know what element it is because it tells you it has how many protons? 1. And the number of protons is the atomic number, which means all you have to do is go to the periodic table and find number 1. So even though it's called deuterium, it really is still hydrogen, right? Because it has 1 proton. Still has 1 proton, 1 atomic number there on the bottom left. In this case, though, mass number, protons plus neutrons, 1 plus 1 is 2. Up on top would be our symbol for deuterium. Take the top number there, 2 minus 1, gives us our 1 neutron that we find in there. I come over here and go tritium. I don't know what that is, but I see it has 1 proton. Means I should go to the periodic table and find number 1. Once again, number 1 is still hydrogen. So even though it has a funky name, it is still hydrogen. Just glows a little bit because it's radioactive. Not really. But it has 1 proton and 1 atomic number. Here we have for our mass number, 1 plus 2 is 3. So these are the 3 isotope symbols for the 3 isotopes of hydrogen. Guy on the left is hydrogen. Middle one is deuterium. Last one is tritium. Even though they have different names, they're all still hydrogen. And that is because they all have how many protons? They all have 1 proton. And the proton, again, is what determines what element it is. And all I have to do is go to my periodic table and find number 1. Yeah? Any questions on that there? All right, I think we'll lay it up there for today.